So we know that LLMs are trained to predict the next word. When we decode the output sequence, we use the tokens of the prompt and the previously predicted tokens to predict the next word. With greedy decoding or multinomial sampling decoding, we use those predictions to output the next token in an autoregressive manner. But is this the sequence we are looking for considering the prompt? Do we actually care about the probability of the next token in a sequence? What we want is a whole sequence to maximize the probability condition on the prompt, not each token separately. So let's look at why predicting the next token is not the prediction we care about and how we can do better than simply autoregressing by just looking at the probability of the next token. Let's get into it. So we're going to look at the beam search generation strategy, but before we need to understand what we are doing with the greedy search or the multinomial sampling search. In both the greedy search or the multinomial sampling search, we have the model that predicts a probability based on a prompt. So the model is using the prompt and is predicting the probability of a token. In this autoregressive process, we have multiple iterations. In the first iteration, we just have the prompt, and the model is trying to predict the probability of the first token. So here we have the probability of token 1 conditioned on the prompt. And this is what the model is outputting. In the second iteration, we autoregress. We use the token 1 as input to the model. So we condition on the prompt and the token number 1, and we try to predict the token number 2. In the third iteration, we use the token 2. We use it as input to the model. So we use the prompt, the token 1, the token 2, and we want the model to predict the token 3. And we iterate this process until the last element in the sequence. So as the nth iteration, we want to predict the last token, and the prediction is based on the knowledge of the prompt, the token 1 to token n-1. So we have this autoregressive decoding of the output sequence, where little by little we learn the different tokens in the output sequence. With the greedy search, we maximize the probability at each iteration, where with the multinomial search, it's a bit softer, where we look at the probability distribution of all the words at each iteration. But this is not the probability we actually care about. What we care about is that when we use a prompt, we want to maximize the probability of the output sequence. We don't care about the probability of the next token. We care about the fact that the output sequence is meaningful if we condition on a specific prompt. So we want to find the output sequence that maximizes the probability conditioned on a specific prompt. That is the probability we care about. Another way to put it is that conditioned on a specific prompt, we want to find all the different tokens from 1 to n that maximize this probability. So we want to find the sequence of tokens that maximize this probability conditioned on this specific prompt. So that is the probability that we want to maximize. And it is different from maximizing the token generation at each iteration. So this is the probability that we want to maximize, and let's try to understand how this probability relates to what the model can calculate. The model is good at calculating the probability of the next token. So how do we use that to calculate that specific probability? Well, let's decompose this probability. We're going to use this property of probabilities. When we look at this probability from token 1 to token n, this is equal to the probability of the token n conditioned on the prompt and the other tokens times the probability of the token 1 to the token n-1 conditioned on the prompt. So we are basically decomposing this probability into a product of two other probabilities. So we have the probability of the last token conditioned on all the other tokens and the prompt, and we have the probability of all the tokens from 1 to n-1. So you can notice that this probability here, the probability from token 1 to token n-1, is very similar to the initial probability from token 1 to token n, but we just lost the last token. Well, we're going to apply this decomposition iteratively. So let's decompose this last probability here, and you can see that we still have the probability of the last token based on the other tokens, but we now have the probability of the token n-1 based on all the other tokens but the token n. And again, we have the probability from token 1 to token n-2. So you can see that we have a pattern here of decomposition of the different probabilities. So now the probability is decomposed into 3 different probabilities. And it happens that I can decompose this probability from token 1 to token n as a product of probabilities of predicting the next tokens. And every time the probability of predicting the next token is conditioned on the prompt and the previous tokens that happen in the sequence. So here this is the probability of token n, and this is dependent on the prompt and the tokens from 1 to n-1. Predicting the token n-1 is dependent on the prompt and the tokens from 1 to n-2. And predicting the token 2 is dependent on the prompt and the previous token, which is token 1. And predicting token 1 is only dependent on the prompt. You can see that I can construct the actual probability that I care about, which is the probability of generating all the different tokens, as a product of all the probabilities of generating the next token. And the probability of generating the next token, this is what the model is predicting. So we can use what the model is predicting by using this product to compute the probability that we actually care about. So let's try to understand why this matters. So let's imagine that we first perform a greedy search. And in the first iteration, the model is predicting this vector of probabilities. If I use greedy search, I will use U as the next token because it has the highest probability. So I pass U to the model, and in the second iteration, the model generates a different probability vector. But this time the word with the highest probability is the word get. And you can see that if I apply the greedy search, I will get the sentence you get. The probability of generating the first token times the probability of generating the second token is equal to 0.16 times 0.16, which is those two different values that I have at those two different iterations. And this gives me a value which is 0.0256. Okay, this is just the value, and we're going to go back to it in a second. Now, let's imagine that it exists a better search to find the better sentence. So in the first iteration, we have the same vector that we have here, the vector that we had in the case of the greedy search. But let's assume that I choose the word at instead of the word you. So the word at has a probability of 0.14, whereas the word you has a higher probability of 0.16. But yet, I'm going to choose the word at for the next iteration. I include the word at in the model, and in the next iteration, the model predicts a different vector of probabilities. So this vector of probabilities is different from the one that we saw in the case of greedy search. And the reason is that we chose a different word in the first iteration. And let's say that if I were to choose the word him in the second iteration, I would get a sentence at him. And I could compute the probability of this sentence. So the probability of having the first token times the probability of the second token is equal to 0.14 times 0.19, which gives me a value of 0.0266. 0.0266 is a higher value than the value we saw in the case of the greedy search. This means that this sentence has a higher probability to be relevant considering the prompt that we have. And the only reason we got this higher probability sentence is that in the first iteration, we chose a word that was not having the highest probability. The problem with that is, what word should I choose in the first iteration? Should I choose every word? So at each iteration, I would need to test every word, and that would make it very impossible computationally. Finding the right tokens considering the prompt is actually an NP-hard problem. Because I will need to include every word at every iteration, this means that the computation resources that I will need would diverge exponentially as I iterate. So I will need a time complexity to compute the right sentence that is exponential with the number of words and iteration. To avoid having to solve an NP-hard problem, we're going to use the bin search generation. So bin search has a hyperparameter that is called the beam size. In this specific case, I chose the beam size to be 4. This means that at each iteration, I choose 4 different candidates that maximize the probability. Those are the 4 different words with the highest probabilities in our probability vector. And what I'm going to do is I'm going to test all those candidates. So I'm going to use the 4 different words and I'm going to include them into the model 4 different times to test the 4 different candidates that come from this test. At the second iteration, I have 4 different probability vectors for the next token. And in each of those vectors, I can choose 4 different candidates for the next word. And I just choose the 4 different words that have the highest probabilities in each of the different vectors. Here I chose beam size equal to 4, but beam size is a hyperparameter, and I could choose any number of candidates. Here I'm going to continue with this beam size equal to 4 example. In the third iteration, I have 16 different candidates. If I continue like that, the number of vectors that I will need to calculate will grow exponentially. So instead of continuing like that, I'm going to choose the 4 best candidates in those sets of vectors. And to choose the best candidates, I choose the candidates that maximize the probability of the whole output sequence up to now. For now, I have 3 different tokens in that output sequence. What are the 3 different tokens that maximize the probability of this output sequence so far? Here I have 4 different candidates that maximize this output sequence. And I can continue. I can use each of those different candidates to generate the 4 different vectors for each of those candidates. Again, I will have 16 different vectors in the 4th iteration. So what I do is I choose the 4 different candidates that maximize the probability of the whole output sequence up to the 4th iteration. So what are the 4 different tokens that maximize the probability of this output sequence so far? And obviously, I repeat this process up to the nth iteration. And I try to find the different tokens that maximize the probability of the output sequence itself. In the end, I just choose the n different tokens that maximize the output sequence up to the last token. In the end, we just choose a set of n tokens that maximize the probability of the output sequence conditioned on the specific prompt. So there are a lot of advantages to beam search. Beam search strikes a balance between the greedy search efficiency and the ability of exploring multiple paths. It generally produces better results than greedy search without the computational expense of exhaustive search. It is flexible through the beam size. It's also called the beam width. The beam width is a tunable parameter. A larger beam width allows the algorithm to explore more paths, increasing the chance of finding a better sequence. It is good for long sequences. Unlike greedy search, beam search can better handle longer sequences as it maintains multiple candidates at each step and can therefore avoid local minima better. It is very useful in structured prediction tasks. It is particularly effective in tasks like machine translation, speech recognition, and summarization, where the structure and coherence of the entire output sequence is important. It can also be combined with sampling. So we can perform beam search by using the multinomial sampling that we saw earlier, by selecting the next token using these sampling techniques. But there are also some problems with beam search. So despite keeping multiple candidates at each step, beam search can still converge to suboptimal solutions. It is not guaranteed to find the most probable sequence, especially with a limited beam width. It has a higher computational cost. The cost increases with the beam width. A larger beam width requires more memory and computational resources, as the algorithm needs to evaluate and store more candidates at each step. It has also a length bias. Beam search has a known bias towards shorter sequences. This is because shorter sequences tend to have higher cumulative probabilities, and the algorithm may favor them over longer, more appropriate sequences. It has a lack of diversity. The top sequences in beam search often differ only slightly from each other, leading to a lack of diversity in the generated text. This is particularly problematic in applications like dialogue generation, where we prefer varied responses. It is heuristic in nature. As a heuristic algorithm, beam search does not always provide guarantees about the quality of its results. The performance can vary significantly depending on the specific task and data. Deciding when to end the sequence can be challenging. If the model decides to predict the end of sequence token, it can truncate a potentially good sequence. So beam search, with its ability to balance between quality and computational efficiency, is a powerful tool in the arsenal of text generation techniques. However, its effectiveness is often tied to the choice of beam width and the specific nature of the task at hand. Understanding its limitations, particularly in terms of length bias and lack of diversity, is crucial when employing this method in practical applications.